Morning. Can we begin? Till almost exactly 100 years ago, astronomy dealt with measuring positions and motions of objects. That is all. Then, after the spectacular discovery by young Fraunhofer, the dark lines in the spectrum of the sun, the subject of astrophysics was born. So today, one is interested in understanding not just the position and motion of celestial bodies, but their nature, their chemical composition, the mechanism of radiation that emanates from them, and so on. And since almost all the information we get about celestial objects is through radiation, I thought it would be worthwhile to review the fundamental principles underlying absorption and emission of radiation. Now, this is something that all of you have read, but I don't think it'll hurt to revise it once more, or perhaps see it in a slightly different context, in the context of astronomy. So let us look at the sun. And the first thing that strikes us about the sun is, although it is a gaseous body, it appears to have a very sharp surface. We need to understand why it appears to have a sharp surface. The second thing is, when you look at the sun during a total solar eclipse, you see emission from the rim of the sun. This was first seen around 1868, not far from Bangalore in Andhra Pradesh. We'll come back to that. This is called the chromosphere, chromo for color, because one saw spectacular colors on this chromosphere. And during totality, one sees the corona. I remember a long time ago attending a lecture whose title was "The Sun We Live In," because the sun doesn't end there, the sun extends right up to the earth and beyond. All right. The first thing you notice about the sun when you look at a white light image is that the limb of the sun appears darker than the central portion of the sun. We need to understand this. The second thing is, if I point the slit of the spectrograph to the limb of the sun, like point B there, what I see are emission lines, like from the tube light. But when I point the slit of the telescope to the disk of the sun, anywhere in the disk of the sun, I see absorption lines and not emission lines. So we need to understand why we see absorption lines and not emission lines. Now, in 1868, in Guntur in Andhra Pradesh, not far from here, astronomers from all over the world assembled to study the total solar eclipse in the month of August, if I'm not mistaken, in 1868. And spectrograph was available by that time, and therefore, during the 100 seconds or so of totality, people tried to capture the spectrum of the chromosphere of the sun. Here is a modern spectrum of the chromosphere of the sun. That rim is dispersed by a grating or a prism. Now, the French astronomer by name Janssen discovered that in this emission spectrum during totality, all the usual lines that one sees in the laboratory were detected. But in addition, there was a very strong line in yellow, very close to the D1, D2 lines of sodium. A very strong line which had not been seen in any spectrum till then. A few weeks later, the Scottish astronomer Sir Norman Lockyer was convinced that a new element had been found in the sun which had not been found on Earth. And he called it helium, after the Greek word helios for the sun. Some 18 years later, Ramsay, the famous chemist in England, discovered helium among the rocks in the mountains. And then Ramsay and Lord Rayleigh, whom we think of as a great theoretical physicist, analyzed this gas, and Lord Rayleigh measured its atomic weight, specific heat, and so on. So in fact, Lord Rayleigh's Nobel Prize is for chemistry and experimental chemistry and not for theoretical physics, for which he is so renowned. When we look at the sun, we should remember that the photons that hits our eye left the center, excuse me, I keep pressing the wrong button. The photons left the sun a long time ago. Although the photon takes only 8 minutes to travel between the surface of the sun and the earth, it takes a very long time to diffuse from the center where it is produced in nuclear reactions and reaches the surface. Now, we will discuss this in the next lecture next week. Because the interior of the sun is rather opaque to photons, the mean free path of the photons is only about half a centimeter. Therefore, it is a long and tedious random walk for the photon till it reaches a point after which there is very little scattering, and then it travels at the speed of light to wherever it goes. Now that point, that surface, that imaginary surface, is called the surface of last scattering. In other words, the photon may undergo 1 or 2 scatterings after that, but scattering is no longer very significant. It can be assumed to travel at the speed of light. And that imaginary radius is called photosphere, and so that is the apparent surface of the sun that we see. It is the surface of last scattering. In other words, if I were to shine this laser beam onto the sun, the laser beam will get slightly scattered, but after a while, it'll produce a spot on the sun like this because it can't go any further inside. So the sun appears like a brick wall. Just as this laser beam is stopped by the screen, it will be stopped by the surface of the sun. So you look at it either going in or coming out. The surface of last scattering is the place where significant scattering ends, and that is the apparent surface of the sun. Please remember that this apparent size of the sun depends on the wavelength. If you are looking at the sun with a wavelength of 5,000 or 6,000 angstroms, then the photons will escape when you reach a density where the mean particle separation is comparable to the wavelength of light. But if you're a radio wave with a wavelength of 10 meters, then surely you can't escape. You have to go much further out so that the density becomes so small that the interparticle spacing becomes comparable to the wavelength of light. Only there, scattering is no longer important. So if you go to Gauribidnur, which is 80 kilometers from here, and look at the sun with a radio telescope, it'll appear 3 times bigger. Okay, because the wavelength is 10 meters. So the concept of photosphere is obviously a function of wavelength. Now, in the case of the sun, if you do this simple estimate of random walk, you can convince yourself that it takes a photon about 30,000 years to diffuse from the center to the surface of the sun. And then, of course, it takes only 8 minutes to reach the earth. Now, this 30,000 years may not sound very impressive to you, but in the case of a star which is 10 times more massive than the sun, and therefore roughly 10 times bigger, photons will take many millions of years to diffuse from where they are created to the surface. All right? So it's like this. If you're baking a 1 kilogram cake, and let us say it takes 1 hour, to bake a 2 kilogram cake will not take 2 hours. Think about it. In a random walk, there is a square root that comes in. Okay, so the escape time from a massive star, 10 times more massive than the sun, can be of astronomical magnitude. Now let us go back to the limb darkening of the sun. Now I would like to convince you our understanding of the principles of absorption and emission of radiation came from understanding this darkening of the limb of the sun. Let's try to understand this. Let us say we look at the disk of the sun towards the point A. So I'm looking at it from here, I'm looking at that point. Okay, the two pictures are rotated by 90 degrees. So the photon that reaches my eye from the point A, that point, comes from an imaginary surface such that the probability of scattering of a photon from that point is negligible, and therefore it escapes to infinity. So when I look at the disk of the sun, I'm really seeing the point A. But when I look at the limb of the sun, point B, I'm looking at an imaginary surface of a much larger radius. Why is that? Because when I look at the atmosphere, that's why the setting sun looks red, whereas the sun overhead doesn't look red. When I look in this direction, there is more path length of the atmosphere. There is more dust in the atmosphere. Therefore, since photons have to reach a point where the probability of scattering becomes insignificant, photons from over there, where the torch is pointing now, cannot escape, because that path length, the opacity of that path length is much greater. Therefore, I have to look for a point where this arrow length are comparable, and that can only happen from a sphere of larger radius. And since radiation is coming out of the sun and not going into the sun, we can conclude that the interior of the sun is hotter than the exterior of the sun. Therefore, we can conclude that the temperature of this dashed sphere is lower than the temperature of this solid sphere, which is higher. And Kirchhoff taught us that the luminosity of a hot body depends upon the fourth power of the temperature. Therefore, the limb of the sun appears darker simply because when you look at the limb, you're really looking at the slightly outer layers of the sun, which are cooler compared to this. So this explanation was first given by the great theoretical physicist and mathematician Carl Schwarzschild, whom I referred to in the first lecture. And the subject of radiative transfer, much of what I will say, began with this explanation. Now let us try to ask the question, how hot is the sun? Now, I would like to convince you that it is extremely elementary to estimate the interior temperature of the sun just sitting right here, okay, with no astronomical data required. Let's try to understand that. Let me first remind you of the Virial Theorem. The Virial Theorem is something that you would have encountered in mechanics. It's a very powerful theorem which says that under suitable circumstances of steady state, the total energy of the system must be equal to 1/2 the potential energy. Now, if you haven't encountered this theorem, let us test it out. Let us test it out with a simple problem of Newtonian mechanics. There is the sun, capital M, around which there is a planet, small m, going around. Well, the total energy of the system, of the satellite, is the kinetic energy, 1/2 mv squared, plus the gravitational potential energy, which is minus gmm over r. So that is the total energy. Now this involves the velocity as well as the distance. So let's get rid of the velocity by using the force equation, which says that the centrifugal force must be balanced by the gravitational force, mv squared by r is equal to gmm over r squared. If you simplify that, you get the total energy is equal to 1/2 of minus gmm over r, or in other words, that's equal to 1/2 the potential energy. In other words, the total energy of the satellite is equal to 1/2 the gravitational potential energy. So this is a simple proof of Virial Theorem in a problem which we learned in school. Now let us apply this to the sun. The total energy of the sun is the sum of the thermal energy of the particles that constitute the sun plus the gravitational potential energy. Therefore, the Virial Theorem says that the sum of the thermal energy of the particles plus the gravitational potential energy of the sun must be equal to 1/2 the gravitational potential energy of the sun. Okay? Now let us take the gravitational energy on the left-hand side to the right-hand side, and then we simplify the equation to read the thermal energy of the sun is equal to minus 1/2 the gravitational potential energy. It's a good thing there is a minus sign there, because the gravitational potential energy itself is negative, and therefore the right-hand side is in fact a positive number. Therefore, Virial Theorem says that the thermal energy of the sun is equal to 1/2 the gravitational potential energy. Now, what is the gravitational potential energy of the sun? Well, let's try to estimate it. The best way to estimate it is, let's take the sun and mentally split it into two halves, each with a mass m/2. Therefore, the potential energy of attraction between these two is minus g m/2 m/2 by r, which is, I separate them by a distance which is equal to the radius. Forget about halves and so on. The gravitational potential energy is equal to g m squared divided by r. Okay? Now, if you use calculus, you will get a number in front, and I leave that as an exercise for you. Okay? Just as moment of inertia is mr squared, it could be 2/5 mr squared or 3/2 mr squared. You have to use a little bit of calculus to do that. But from a dimensional point of view, the potential energy is gm squared over r. So sitting here on Earth, because I know Newton's constant of gravity, I know the mass of the sun from Kepler's laws, and I know the distance and therefore the radius of the sun, I know the internal thermal energy of the sun. Okay? Now the internal thermal energy of the sun is equal to the number of particles in the sun, capital N, which is about 10 to the power 57 particles, multiplied by the average energy of each particle, which is 3/2 kT. Therefore, N times 3/2 kT is equal to 1/2 gm squared over r. Now, if you substitute for the number of particles, you know the mass of the sun, assume it's made up of hydrogen, therefore you know it is 10 to the 57 particles. Substituting for g and the mass of the sun and the radius of the sun and Boltzmann's constant, you get the temperature of the sun as 10 million degrees Kelvin. Isn't this astonishing? Isn't it a beautiful result? Sitting right here, we are able to estimate the average internal temperature of the sun, which is 10 million degrees. So there is the picture of the sun. Most of the sun is at a temperature of 10 million degrees. The center of the sun is at a temperature of 15 million degrees, so that's not bad estimate. It's just that the sun is surrounded by a thin blanket where it is atoms are still present, namely electrons bound to the nuclei, and that leads to the temperature dropping very rapidly to 6,000 Kelvin, which is the temperature that we see. Because the black body spectrum peaks around yellow wavelength, and that tells us from Wien's displacement law that the surface temperature is 6,000 degrees. I am not going to take the time to explain why the temperature suddenly drops in the outer regions, and that happens very, very quickly. So for our practical purposes, that is just a thin blanket, but most of the sun is at an average temperature of 10 million degrees. Now, let us get down to the fundamental principles that Carl Schwarzschild was the first person to investigate concerning the principles of radiative transfer. Now, I want to introduce certain definitions, and I would like you to write it down very carefully. It is, dimensions are extremely important. Okay? Let us consider a unit area A through which radiation is flowing. Let n be the normal to this unit area dA. And let us consider a small solid angle d omega about this normal to the surface n. The energy crossing this area dA in time dt in a frequency range d nu and into the solid angle d omega is given by dE. dE is equal to some animal I nu into dA into dt into d nu into d omega. Therefore, this I nu has the dimension of per unit area, per unit time, per frequency interval, per unit solid angle. And this quantity goes under the name of specific intensity or brightness. Specific intensity or brightness. Now, the fundamental thing about this is that this brightness does not decrease with distance. We loosely say intensity decreases 1 over r squared, but not the intensity defined in this particular way. The difference between the conventional definition and this is the presence of the unit solid angle, d omega there. So I don't care how far that object is. The energy radiated into your unit solid angle never decreases. Okay? So when astronomers say brightness, they are referring, when they talk of brightness of a star, they are not talking of brightness as defined by Oxford Dictionary, they are talking of brightness as defined by this equation. For those of you who are in a more advanced stage in your education and more interested in mathematics, convince yourself that this quantity I nu by nu cube is a Lorentz invariant. Okay. We are not concerned with it right now. What that means is sometimes when we look at quasars and objects like that, these objects, there are motions which are relativistic. So we know in relativity, the length of the object appears different, the rate of ticking of the clock appears different, brightnesses will also appear different. And at that time, if we ever get to that point to discuss quasars, remember that this quantity I nu over nu cube is a Lorentz invariant, and I recommend that you try to convince yourself of that. Now, very often when we learn physics, we are never introduced to this concept of specific intensity. We talk of the radiation field U nu into a solid angle d omega. What is the relation between the specific intensity and the energy density U nu? Well, very simple. Please remember, I nu is related to the energy crossing this area in a unit time. So let us construct an imaginary cylinder of area d, unit area, and length c times dt, where c is the velocity of light. Therefore, all photons in that cylinder will cross this surface in a unit time. Therefore, the relation between I nu and c nu is that there is a velocity of light that is coming in here. So convince yourself that dimensionally the velocity of light must come in. So when we write Planck's law, as we will very soon be writing Planck's law, we write in terms of the energy density. We write it in terms of U nu and not in terms of the specific intensity. But the two are obviously related. Now let us introduce the concept of the emission coefficient, or more specifically, the spontaneous emission coefficient J nu. Now how is J nu defined? J nu is defined by that equation. J nu is the energy emitted per unit volume, per unit solid angle, per unit time. So dE is equal to J into d nu into dV into dt into d omega. Dimensions are extremely important. The dimensions of the emission coefficient is erg per centimeter cube, per second, per frequency interval, per steradian. Now, if you have a beam of cross-section dA, as shown in that cylinder at the bottom of the slide, then the intensity added to the beam, specific intensity added to the beam over a length ds is given by di nu is equal to J nu into dl. So that is the relation between the specific intensity and the emission coefficient. You will appreciate that the energy crossing a unit surface which is defined in terms of specific intensity, depends upon what is emitted and what is absorbed. So I am introducing the concept of emission coefficient here. So now let me introduce the absorption coefficient. The absorption coefficient is traditionally called alpha. It is obviously a function of frequency, alpha nu. Alpha nu is defined in terms of the loss of brightness in a beam as it travels a length ds. It is the loss of intensity as it traverses a length ds. Therefore, the specific intensity di nu which is lost is equal to minus sign because you have lost intensity, alpha nu into I nu into ds. Okay? So obviously, the dimension of the absorption coefficient alpha nu is per unit length, per centimeter. Now, what is this absorption due to? Well, we will not pause to discuss that in detail right now, but let us assume that it is due to some scatterers, which absorbs or scatters the beam off the principal direction. And let there be n such absorbers or scatterers per unit volume. And let the cross-section of each one of them be sigma nu. The dimension is square centimeter. Cross-section is an area. Please remember, this cross-section is not just the physical, geometrical cross-section, because if you're talking of electron, then you're talking of electromagnetic interaction with the electric field, and therefore it is the effective cross-section for the process. Therefore, this absorption coefficient alpha nu is n times sigma nu. N is number per centimeter cube. This is centimeter squared. Therefore, the right-hand side has the dimension of 1 over length, as it should have. Okay? So now we have dealt with all the important definition. We have dealt with the absorption coefficient. We have dealt with the emission coefficient. And we have defined the specific intensity. Now we write the fundamental equation of radiative transfer, which is given by the first equation over there. It says, you can either take the ds from the denominator to the right-hand side. That is where it was. I've just brought it to the left-hand side. Therefore, the change in the specific intensity in a length ds is equal to the amount that is absorbed in that length ds plus the amount that is added in that length ds. The first is minus alpha nu I nu, and the second is the J nu. The second term does not involve the specific intensity because J nu I defined as the spontaneous emission coefficient. It is independent of the emission that is coming from somewhere else. Now let us introduce a very important concept in astronomy, also in nuclear physics, which is called as the optical depth. It is usually denoted by tau. It's also a function of frequency. Now that tau nu is simply an integral over the path from S0 to S of the absorption coefficient. In other words, if I construct a cylinder of unit area from my eye to the source, it is the integral of the absorption over that length. We define the absorption as per unit length. So it is the integrated absorption over a column length which goes from the observer to the source. Okay? So the optical depth is a dimensionless number. It is an integral of the absorption coefficient. When the optical depth is greater than 1, we say the medium is optically thick. If the optical depth is less than 1, we say the medium is optically thin. Okay? If you go to Uti, where there are these cosmic ray experiments going on, they will talk about the absorbers as grammage. They will say so many grams of material, the equivalent to so many grams of lead are there of the scatterers. Okay? So people are interested in this concept of optical depth, not just in astronomy, but in nuclear physics, reactor physics, cosmic ray physics, and so on. Now, I hope you had enough time to write down that equation, and I have rewritten that equation on the top for your convenience in case you missed it. Now, it is very often written in a slightly different form by dividing the left-hand side and the right-hand side by the absorption coefficient alpha nu. If I divide by alpha nu, I will have on the left-hand side denominator alpha nu into ds, which is the optical depth d tau. So the equation of radiative transfer, which is written over there, can be rewritten in this form, which is the derivative of the specific intensity with respect to the optical depth is equal to minus the specific intensity plus S nu. S nu is simply J nu divided by alpha. Now, this is very often in physics book referred to as the source function, or it is also referred to as I nu B, B for body. Oh, Okay. So this is the equation of radiative transfer. This is the primitive form of the equation of radiative transfer. Dividing by alpha nu, I get di nu by d tau nu is equal to minus the specific intensity minus the intensity contributed by the body itself. Now that equation will become much more transparent to you if I integrate it. I have rewritten that equation here from the previous slide, and I have redefined for you what this I nu B is. I nu B stands for I nu body. That is the specific intensity radiated by the body at the frequency nu. That is the ratio of the emissivity to absorptivity. Emissivity to absorptivity. Now let us integrate that equation. I bring the right-hand side to the bottom here, take d nu to that side. I will get a logarithm. If I get rid of the logarithm, I will get an exponential. And I will find I nu minus I nu B is equal to I nu 0 minus I nu B. I nu 0 is the incident specific intensity multiplied by e to the power minus tau nu. Now, before we try to understand whether this equation makes sense, let us simplify it by combining the terms and write the equation of radiative transfer in its final form, the form that I will use, the form that is always used in astronomy. So you don't have to remember all the things that went before it. Please write down this equation and try to understand it in your own terms. I nu is equal to I nu 0 e to the minus tau nu plus I nu B into 1 minus e to the power minus tau nu. What the hell does it mean? What is it trying to tell us? So right on the top is the same equation of radiative transfer. I have copied and pasted here for your ready reference. Let us look at the first term here. Here is a body. This green cylinder is the body. Incident on it is a specific intensity I nu 0. It goes through the body and comes out. And what we are saying is that this incident specific intensity is attenuated by the body, and I get e to the power minus tau nu. I can chop up this body into a series of slices like this. Each will absorb alpha nu ds, and then if you sum the series, you get an exponential. Okay? So convince yourself that this equation makes sense. That is the first term. So the first term is the incident specific intensity attenuated by the body. But the body is not passive. The body also emits radiation. That is given by I nu B into 1. But the body also absorbs what it emits. The first slab here emits something. The second slab absorbs part of it, but it also emits. Third slab absorbs part of it, it also emits. If you sum the series, you'll get 1 minus e to the power minus tau nu. Therefore, the first term is the incident intensity attenuated. The second term is the intensity added by the body, but also absorbed by itself, self-absorbed by itself. So that is the equation of radiative transfer. Okay? At some stage, we owe it to Carl Schwarzschild for teaching us all these things. Okay? Now, let us look at this equation in various limits. When the optical depth is very small, when the optical depth is very large, and so on. Let us first look at this equation when the optical depth is much greater than 1. So that is the scenario, incident specific intensity. There is a body and there is a specific intensity coming out. And that's the basic equation. When optical depth is infinity, the first term goes to 0. What is the meaning of the first term going to 0? I can't see what that place where the coffee and tea was served because that wall is opaque. So the only radiation I will see is the radiation from the body. Therefore, the first term is 0. And when tau is infinity, e to the power minus tau is 0. Therefore, what I will get is just the specific intensity emitted by this body. And that body is at a certain temperature. What is the specific intensity emitted by that body? That is what Kirchhoff taught us and Planck derived. That is equal to 2h nu cubed by c squared 1 over e to the power h nu over kt minus 1, which is the black body spectrum. In other words, when an object is opaque, you only see the atoms on the surface. When you see the sun, you don't see the interior. You only see the surface. So the luminosity is sigma t to the power 4 into 4 pi r square, right? So that is black body radiation. So what we are saying is, when this body becomes opaque, forget about the radiation that is incident on the left. What it will radiate is what it will radiate as a black body at a temperature T. And that is the specific intensity. Now, some of you whose memory is very good will say that that is not Planck's law. Planck's law, as I remember it, and as you should remember it, will have 8 pi and it will have c cubed, and not 2h nu cubed. What is the connection? Well, we already said that there is a relation between specific intensity and the energy density, and that involves a c. Therefore, you knew when we write Planck's law in terms of energy density, c comes as the denominator, therefore c squared becomes c cubed. That is energy density into a solid angle omega. But if I want to integrate over all the solid angle, I get 4 pi, therefore 2 becomes 8 pi. So that is why you get in Planck's law 8 pi by c cubed. Okay? So this is Planck's law, right? It is just that the stated in terms of specific intensity. But we know how to connect specific intensity to energy density of the radiation field. So I have written it for your convenience. Planck's distribution is given on the top, and because I will refer to it towards the end of this lecture, let us take the limit of that when h nu over kt is much greater than 1 or h nu is much greater than kt. In that limit, this 1 in the denominator can be ignored, and this e to the power h nu over kt can be taken upstairs, and it becomes e to the power minus h nu over kt. And this is known as Wien's formula. It was first derived by Wien before Planck, and therefore he didn't know what this bracket was. He called it alpha. Okay? It was Planck who derived what alpha was, and you notice, obviously Planck's constant couldn't have come in before Planck 1900. Okay? So in Wien's formula, we are really referring to nu cube e to the power minus h nu over kt. It is the high frequency part of the black body spectrum. I have written this for a specific reason. We will come to that in the end. The significance of that was first appreciated by Einstein. So the famous Wien's displacement law, which you have all studied in pre-university, which says that the maximum of the black body spectrum occurs when h nu is of the order of kT, or lambda max is inversely frequency. The frequency at which the maximum occurs is proportional to the temperature. The wavelength at which the maximum occurs is inversely proportional to the temperature. And in CGS units, this wavelength in centimeters is 0.29 divided by the temperature in Kelvin. Okay? And you're all familiar with this displacement law. And this will play a very important role when we discuss cosmology at some stage. Here is the black body spectrum drawn for a variety of temperatures ranging from 0.1 Kelvin, 1 Kelvin, 10 Kelvin, a billion Kelvin, and 10 billion Kelvin. So you see the maximum shifts to higher and higher energies. So when the universe was about a second old, the peak of the black body spectrum was in the ultra high energy cosmic rays. Today, the peak of the black body spectrum, the temperature of the universe is 3 degrees, is in the microwave region. So this is Wien's displacement law. And here is the most perfect black body spectrum that we have seen till today, the spectrum of the cosmic microwave background radiation, and it is fitted to a temperature of 2.74 Kelvin. And I would like to stress that the error bars have been drawn in this picture. Okay? So this includes the error bars. Okay, this is all very familiar things for you. Now, let us take, we have dealt with the case where the body is opaque, where the optical depth is infinity. Now let us take the case where the optical depth is not infinity, but is less than 1. Like the air in this room is semi-transparent, depending on what wavelength. At visible wavelength, it is completely transparent. Okay? So let us look at this step by step. We already saw that in the limit when the optical depth is very large compared to 1, the specific intensity is simply given by that emitted by the body as it would if it were a true black body at a temperature T. But I want you to now look at the optical depth much less than 1. When the optical depth of this body is much less than 1, then you can expand e to the power minus tau nu. 1 and 1 cancels. The first non-trivial term is tau nu. And we'll stop there because tau nu squared can be neglected because tau nu is much less than 1. Therefore, the specific intensity of a body, by the way, there is no background radiation. I'm talking only about the radiation from a body whose optical depth is very small. Therefore, the specific intensity is tau nu into I nu b. In other words, if this body is diffuse or not opaque, it will not emit black body spectrum. It will emit the black body spectrum multiplied by tau nu. Therefore, for an optically thin body, the radiation intensity at every frequency is always less than that from a black body at that frequency. Okay? And this is called the black body limit. So here I have written the same thing. I have summarized for you in words. The intensity from an optically, that's a mistake, an optical, no, this is correct. I am repeating the whole thing again. The specific intensity from an optically thick body approaches the black body value. It can never exceed this. It can never exceed this. Okay? So no matter what the mechanism of radiation is, the object cannot radiate at any frequency what it would radiate if it behaved like a black body. So it's a very powerful theorem that I'm stating here. So one picture is worth 10,000 words, the ancient Chinese saying goes. So what I have plotted here is the black body spectrum at some temperature T. I'm saying that when the optical depth is very small compared to 1, the specific intensity will be tau nu into I nu b. So it can be this green skyscraper or this green skyscraper or this one, but it can never be the red skyscraper. Point I'm making is at no frequency can a body emit more than it would emit if it behaved like a true black body. Okay? So this is called as the black body limit theorem. If it did, you could run a perpetual motion machine. Now in practice, this is what happens. Let us say that I have a tube light, or I have a nebula in the interstellar space, the Orion Nebula or some nebula that you may be familiar with. What you will find that its intensity versus frequency is this dashed green curve. That body is at a certain temperature T. What do I mean by the temperature T? It means that the velocities of those particles are given by Maxwell's velocity distribution at that temperature T. But that body is not opaque. It's like the tube light here. Therefore, the intensity at any frequency and every frequency will be less than what it would emit if it were a true opaque body. But you notice here I have written very carefully the dashed curve and the solid curve merge. Why is that? That's simple common sense. No matter how diffuse the body is, I can go to low enough frequencies so that the mean distance between the particles becomes comparable to the wavelength. There the body will be opaque. So I'm saying in this limit of very low frequencies, all bodies will be opaque at any, up to certain frequency, right? Therefore, if I take a nebula or the tube light or whatever it is, its spectrum, not surprisingly, in the Rayleigh-Jeans part, will hug the true black body spectrum. And then, of course, it will deviate. The maximum will be underneath one another. Because the maximum always occurs when h nu is of the order of kt. That doesn't change at all. Okay? Now, there is a fraud here. What about a laser or a maser? Take this thing. This is at a temperature of 300 Kelvin, same temperature as my body, what I am holding. Therefore, the intensity of radiation from this cannot exceed the intensity of radiation at the green frequency from a black body at 300 Kelvin. But that is nonsense. That intensity is about 10 billion times more than the intensity of my body at green wavelength. So what is the fraud? Well, the fraud is that a laser or a maser is not an absorber, it is an amplifier. In other words, each layer of the slab adds intensity. So previously we defined the absorption coefficient as the energy taken away minus alpha nu into I nu was the specific intensity taken away. It should not be minus there or plus, or if you want to keep it plus there, alpha nu you would say is negative. Okay? So a laser or a maser is not an absorber, it is an amplifier. And you cannot run a perpetual motion machine here because a laser or a maser manifestly violates thermodynamic equilibrium. There is a population inversion. There are more atoms in the upper level, some metastable state, compared to the lower level. Whereas in true thermodynamic equilibrium, Maxwell-Boltzmann statistics should apply, and the number should decrease as e to the power minus capital E over kt. Okay? So please remember that a laser or a maser manifestly violates this black body limit. Right? Now we get to the absorption and emission lines. Now please remember that up to now, I have not said anything about the physics of the absorption or the physics of emission. But we know that the physics of absorption or emission are to be found in quantum mechanics. In quantum mechanics, there are energy levels. There are only certain green upward transitions that are allowed. There are only some yellow downward transitions that are allowed because energy levels are discrete. Therefore, the absorption coefficient, the emission coefficient, and therefore the optical depth tau nu will all be a function of frequency. At most frequencies, it will be 0. Suddenly, at one frequency, it is non-zero. And when it is non-zero, it will not be a delta function. It will be sort of like a Gaussian or a Lorentzian, because these energy levels are not infinitely sharp. They also have widths, and therefore, these absorption coefficients, tau nu, alpha nu, j nu, they will all not be delta functions in frequencies, but each will have a line shape, as we are familiar. You all know the origin of this line shape. So there will be a spread in the frequencies because energy levels are finite bit. And there may be other processes that produce continuous radiation. For example, when we break our hand or wrist or leg and go to get an X-ray done in a clinic, how are the X-rays produced? X-rays are produced by bombarding a metal sheet with an electron. How does an electron produce X-rays? Well, the electrons are scattered by the nuclei, and they are either accelerated or decelerated, and they produce radiation which is called Bremsstrahlung radiation or break radiation. And that produces X-ray. And that spectrum is continuous. It is not a fixed line. Right? So, what I've illustrated is a quantum mechanical process which involves discrete energy levels, but it doesn't have to have discrete energy levels. Some cases you can have continuous or quasi-continuous energy levels. Let me put it more precisely. You can have a situation where you don't fuss with quantum mechanics, but you can describe it semi-classically. In other words, you say that the energy levels are quasi-continuous. Now, I've set the stage. Let's go back to the fundamental question. We understand why the limb of the sun appears darker. Now, I want you to understand why in 1868 in Guntur, when the sun was covered by the disk of the moon and the spectrum was only of the chromosphere from that point, why they saw emission lines. You now have to explain that. And that explanation is to be found from the same equation of radiative transfer. So now, when you are woken up in the middle of the night, you should be able to write the radiative transfer equation. Not from memory, but I nu is equal to, well, incident intensity, what is absorbed, and then what is emitted by the body and what is self-absorbed by the body. You'll be able to write it all your life once you understand that picture, okay? Let's try to understand this now. Let's go back to the equation of radiative transfer, which is over there. Now, when I look at the sun in that direction, there is no background radiation. There is no radiation coming from there. So I'm talking of radiation that emanates from the rim of the sun. So the first term is 0, it doesn't exist. And since the limb of the sun is a diffuse body, I can expand this in powers of the optical depth tau nu and keep only the first term. And therefore, I nu will be equal to tau nu into what it would radiate if it behaved like a true opaque black body at that temperature T, I nu B. So, one picture is worth 10,000 words. Here is the specific intensity as a function of frequency. We are at that frequency. We are only concerned at that frequency nu. That's the amount of intensity it would radiate if the limb of the sun behaved like a black body, but it is not opaque, so it is not black body. So it is that multiplied, that is the length of the magenta arrow, multiplied by tau nu, which gives me the yellow arrow. So what I will get from the limb of the sun is only that. It will be 0 everywhere. Only at frequencies where the optical depth is different from 0, I'll get a certain intensity smeared off due to various line widths, and that intensity, specific intensity, is equal to tau nu into I nu B. Now, if I increase the optical depth, that intensity will increase because it's tau nu into. If I go on increasing the optical depth, that will go on increasing, but it can never exceed that, which is the black body limit. Okay? So the limb of the sun can never emit more than it would radiate if it were opaque. Of course, it's not opaque. So we now have the explanation. for why, if I point the spectrograph slit to the limb of the sun, I get emission lines, which is where the story began, the discovery of helium and so on, 1868. So now let's ask the other question. If I put the spectrograph slit towards the disk of the sun, anywhere in the disk, I see absorption lines. This is what Fraunhofer found. So let's see why that is the case. Let's go back to the equation, which is the radiative transfer equation, written here again for your convenience. This time I have background intensity, because when I look at the limb of the sun, it is the radiation from the interior of the sun which is going through the outer layers of the sun. Therefore, the picture of the configuration is, this is the outer layer of the sun, this is the radiation emanating from the interior, black body radiation emanating from the interior, and what comes out is the sum of what is absorbed and what is emitted by that body itself. So, since the outer layers are diffuse, once again I expand the optical depth in powers of tau nu. Both these terms I expand, and I write the specific intensities I nu 0. Here if I expand, I'll get 1 minus tau nu. 1 is that term, minus tau nu into I nu 0 is that term. If I expand this, 1 and 1 cancels, so I have only tau nu term. I'll have tau nu into I nu b, that is tau nu into I nu b. Minus into minus is plus. So this second equation is the first equation expanded for small optical depth. Now so what I find is that this is the specific intensity of that frequency it will emit if it were a black body, but something has been taken away from it. Something has been taken away from it, and so the intensity is actually only that much. And if I increase the optical depth, more intensity will be eaten away. And in the limit, when it becomes opaque, I'll only get that radiation from that slab, outer layer. Inside radiation I will not see at all. The outer layers will become like a curtain, and I will only see the curtain. Again, we will encounter this in cosmology when we talk of the surface of last scattering at the age of 300,000 years. Okay? So that is so we now have an explanation for why we see absorption lines and emission lines. So here is a grand summary of my crash course into radiative transfer. If I have an opaque body, it emits a true black body spectrum. If I have a tenuous body at a certain temperature T, it emits a continuous spectrum. It may emit a continuous spectrum, it may not emit a continuous spectrum, but there are emission lines in it. But the intensity of either the continuum or the emission lines can never exceed that of the black body at any frequency. Therefore, this is Kirchhoff's second law, stated in 1859. A rarefied luminous gas emits radiation whose spectrum consists of a series of bright lines, sometimes superimposed on a faint continuous spectrum. Kirchhoff's third law. If a radiation from an opaque body passes through a tenuous body, you see the spectrum of the black body, but at some discrete frequency, the intensity is eaten away by this tenuous body, and you see absorption lines corresponding to the same frequencies that the atom would emit, and this is what Fraunhofer saw. Okay? So that's where matter stood till 2 years after Einstein published his general theory of relativity, and instead of taking a hard-earned vacation, he turned to the quantum theory of radiation. And he published a paper which was a masterpiece in 1917. And I would like to tell you about this paper because this paper contains the first derivation of Planck's distribution. Okay? There's a slight amount of hand waving involved, and that was fixed by S. N. Bose a few years later. But this paper is of fundamental importance, and its significance will become even more apparent to you when we discuss Hawking radiation from black holes. So, now I'll go slowly so that you have enough time to write. Let us consider, as Einstein did in that paper, for simplicity, a two-level atom. There is an upper level M and a lower level N. Now, one was already used to the idea of the concept of stimulated absorption. That means radiation field causes the atom to go from this level N to this level M. And Einstein described this stimulated absorption in terms of a coefficient B. Therefore, the rate of transition from N to M, from the lower level to the upper level, depends upon this coefficient B. It also depends upon the number of atoms which are in the lower level N, and it also depends upon the radiation energy density U nu. Therefore, the rate of stimulated absorption is Bu into N of N. Now, this radiation also tickles atoms which are in this upper level to jump to the lower level, and this is called stimulated emission. And this is what laser or a maser does with supreme efficiency. So the rate of transition from the upper level to the lower level is the Einstein coefficient C multiplied by the number of atoms in the upper level N of M multiplied by the energy density U of nu. This is something that we had appreciated before Einstein wrote this paper. But what he introduced in this paper was this important concept of spontaneous emission. He argued that an atom will jump from the level M to N even if it is not tickled or prompted by an external radiation field. Therefore, why it would jump? He had no answer for that. We found out the answer only in the 1940s. Today we will say an atom jumps from an upper level to lower level spontaneously because of vacuum fluctuations. Okay, these are the work done by Feynman, Tominaga, Schwinger, and various other people, quantum electrodynamics. But long before that, Einstein asserted that there must be such a thing as a spontaneous emission, whose rate is A, and therefore that rate, spontaneous emission, depends on A. It does not depend upon the radiation field because it is spontaneous, but of course it depends on the number of atoms in this upper level M. Now Einstein argued that in thermodynamic equilibrium, the rate of going from the lower level to the upper level must be precisely equal to the rate of coming from the upper level to the lower level. He invoked the concept of thermal equilibrium. Okay? Now, A and B and C are known as Einstein's coefficient, and for our purpose, from symmetry, you will please agree with me that B can be identified as C. Now, thermal equilibrium Einstein said the number of particles in the state M is proportional to e to the power minus Em over kT. The number of particles in the state N is proportional to e to the power minus En over kT. Therefore, the ratio of the number of particles in the state M to the state N is equal to e to the power minus Em minus En over kT. Now, as I already said, at thermal equilibrium, the rate from N to M must be equal to the rate from M to N. What is the rate from M to N? Is A plus C U nu into Nm from the previous slide. What is the rate of transition from the lower to upper level? It is the Einstein coefficient B U nu into the number of particles in the lower level. Now, the above rates are equal if so. That's why I raised this. At this point, let me take you through the algebra. So what we have is A plus C U into N of M is equal to B U into N of N. We will equate B and C by symmetry. Therefore, I have A into number of particles in the state M is equal to B into number of particles in the state N minus number of particles in the state M and a bigger bracket there. Therefore, A over B, the ratio of the Einstein coefficient A over B is equal to, no, something is wrong, right? B times U. Yeah, U is what I want. Otherwise the sign is okay? Correct. Yeah, that's fine. So A over B is equal to, no, I want U. I want to solve for U. Therefore, U of nu, the energy density at a frequency, is equal to A over B. Let's put a bracket there. The number of particles in the upper state M divided by the number of particles in the lower state minus the number of particles in the upper state. Let us divide by Nm. So keep A over B as A over B into 1 divided by N divided by N M minus 1. That, permit me to write here, is A over B into 1 divided by e to the power Em minus En divided by kT minus 1. Right? And that, what is this? This is the energy density at frequency nu. Good. So at this stage, so this is just rewriting it. At this stage, Einstein appealed to Wien's displacement law. What Wien had shown was that at high frequency, the energy density U nu is alpha nu cube into e to the power minus h nu over kT. You remember that? We had written it in the beginning. Therefore, he identified, comparing these two equations, Einstein derived the famous relation between spontaneous emission and stimulated emission or absorption coefficient. So he said A is equal to 8h nu cubed by c cubed times B. And then using Bohr's principle, he said Em minus En must be equal to h nu. And that is Planck's law then. So what I want you to appreciate is for the very first time, Einstein gave a physical reason for why in a black body the spectrum achieves this Planckian distribution. he showed that it is an interplay between stimulated absorption, stimulated emission, and spontaneous emission, with a requirement of thermal equilibrium. And it's truly profound. And his opening sentence of his paper is this: the formal similarity of the spectral distribution curve of the temperature radiation, which is black body radiation, as it used to be called those days, to Maxwell's velocity distribution curve is too striking to have remained hidden very long. Okay? So, black body curve, except there's one slight sloppiness, I'm astonished. It's not Maxwell's velocity distribution, it's Maxwell's speed distribution. Because Maxwell's velocity distribution is centered around 0. Whereas Maxwell's speed distribution, this is, right? Remember that, right? It's a bell-shaped curve. So, what is it? The striking similarity between this and the black body curve couldn't be hidden for very long. So he said there must be thermal equilibrium taking place between energy levels of atoms. And so that is the origin of black body radiation. Okay? So I would like to tell you, underline here as loudly as I can, the moral of this paper by Einstein, which is whenever there is stimulated emission, there has to be spontaneous emission. Okay? And it was this realization that led to Hawking's great discovery. We will come to that. Okay? Now, so you have to know either A or you have to know B. That Einstein could not calculate, because he was actually calculating black body spectrum. For that, you have to use quantum mechanics. And those of you who have studied quantum mechanics or will study will know that this spontaneous stimulated emission or absorption coefficient is related to the matrix element of the coordinate oscillator strength, as it is called, and the square of it. This is if you are dealing with a single particle. Now that equation can be written as E into x. So for a multi-particle system, it is the dipole moment d, which is sum of EI xi, or all I, comes in instead of a single coordinate x, okay, if you're dealing with multi-electron system. Now the important thing for you to appreciate is that in quantum mechanics, radiation is due to change of dipole moment. And that was what it was in classical mechanics, because the famous Larmor's formula of radiation intensity is if you have a particle with an acceleration, the energy radiated per unit time is equal to 2 by 3 c cubed E squared A squared, where A is the acceleration of the particle. So E squared into x double dot whole squared, acceleration squared. That is equal to E into x double dot whole squared. So in other words, that is equal to the electric dipole moment second time derivative whole squared. So, and if you are dealing with gravitational radiation, this term is 0, then you will say it is proportional to the third time derivative of the quadrupole moment whole square, and so on, right? I'm sure either you have studied or you will learn these things later on. Now, to conclude, I want to take a concrete case. The first case that I want to take is the energy level 2p and oneness of a hydrogen atom. This is n equal to 2, this is n equal to 1. Now, you can calculate the oscillator strength because you know the wave function of this level and wave function of this level, and therefore you can calculate the Einstein coefficient A, which is the dimension of second to the power minus 1, or the reciprocal of the lifetime. So the lifetime of this level is about 1 nanosecond. So in other words, an electron left to itself will jump from n equal to 2 to n equal to 1 in a nanosecond. It's similar transition time for various Rydberg levels. Now let us look at the ground state of the hydrogen atom. Please remember the ground state of the hydrogen atom consists of an electron and the nucleus consists of a proton. The electron spin can be like this and the proton spin can be like this, or the electron spin can be like this and the proton spin can be like this. These two will have different energies. And that, those of you who have studied quantum mechanics, is called hyperfine splitting. And the transition probability from that upper level where the electron spin and the proton spin are parallel to the lower level where the electron spin and the proton spin are anti-parallel is not nanosecond, but it is 10 to the 7 years. Okay? And most of what we know about our universe, our galaxy and the rest of the universe, comes by studying the universe with a radio telescope at that frequency, which is 21 centimeter. This is the famous 21 centimeter radiation of the hydrogen atom. However improbable it may be, it is there. The galaxy is blazing in this line. The universe is blazing in this line. Okay? So all this business of dark matter in the universe and all that was discovered using this spectral line. So let me conclude by making a few remarks which you may or may not have heard in this language, but it is worth stressing it. Let me stress what is obvious, that in the ultimate analysis, radiation is by quantum mechanical processes in which the electron makes a transition from one level to a lower level. Now, in an ensemble of atoms or molecules, the occupancy of these energy levels is given by Boltzmann's distribution, e to the power minus E over kT. In other words, you say matter is in thermal equilibrium. Now, in diffuse matter, point number 3, where the optical depth is much less than 1, the photons retain their signature. So when I look at the radiation from this tube light, I know which atom emitted. I know which level to which level it jumped. I know what was the frequency and what was the polarization of the photon, because I can see that. And not surprisingly, the total emissivity is proportional to the total number of atoms in the tube light. That's why a 20-watt tube light is this big, a 40-watt tube light is that big. Intensity is proportional to the number of atoms. Okay? If it's a black body, it doesn't matter if it's this long or that long. At a certain temperature, it will only radiate the same amount per unit area. Now, in an opaque body, tau much greater than 1, the radiation loses all memory during the process of multiple absorption and emission. This is the stimulated absorption, stimulated emission, spontaneous emission. And this was Einstein's point, although not stated in this language. Radiation remembers only, please remember, first of all, when it comes out of an opaque body, all we see are the atoms on the surface. We don't see the atoms inside which emitted the photon. We see only the surface of last scattering. And it has lost all memory. The only thing the photon remembers is the thermal equilibrium, that the matter that it collided with got absorbed and re-emitted, got absorbed and re-emitted, was in thermal equilibrium. What do I mean by that? At a certain temperature, what I mean by that is that the distribution of population is given by e to the power minus E over kT. That T it remembers and doesn't remember anything else. Therefore, the radiation is characterized by only the temperature and nothing else. This is what Kirchhoff said in 1859. He said, the spectrum of radiation by a black body is a universal function of temperature alone. Because if two black bodies at the same temperature emitted differently because one was gold and one was platinum, then I could connect the two and run a perpetual motion machine between two bodies at the same temperature, which you are not allowed to do. And that was Kirchhoff's argument. Therefore, the spectrum of radiation from a black body cannot depend on any property other than the temperature. And therefore, this spectrum of radiation has lost all its memory, and it remembers only the temperature of the body with which it itself came into thermal equilibrium. Sounds obvious to you, perhaps, but yeah. But please remember that in most astrophysical situations, matter and radiation do not come to thermodynamic equilibrium. In the sun, because the sun is opaque, as we will see next Wednesday, matter and radiation come to equilibrium. But in a nebula or this neon sign in a shopping center or this tube lights, matter and radiation do not come into equilibrium. There aren't enough absorption and re-emission. Therefore, the temperature of the radiation need not be equal to the temperature of the matter. So, Shakespeare, right? Rose by any other name will still smell sweet, right? Or somebody said rose by any other name is still a rose. But that's not true of temperature. And on that note, I would like to end by stressing this, because this is something that you may not have heard before. You have to ask the fundamental question, what is temperature? Right? You have to ask, what is temperature? So you better have an answer for that. So the first time we encountered the concept of temperature was, today we will call it kinetic temperature. That kinetic temperature is essentially the width of the Maxwell's velocity distribution. Okay, this width, sigma, is equal to square root of kT over m, if I'm not mistaken, but please check and correct it. Okay, I wrote it from memory. All right? So at a lower temperature, Maxwell's velocity distribution is more squeezed and taller, and the Gaussian gets broader and broader. So that's what we mean by kinetic temperature. Or in other words, the average energy of the particle is 3/2 kT. So that T is kinetic temperature. In other words, that's a measure of the motion and the thermal equilibrium. Then there is this concept of excitation temperature. Which is called T excitation. What is that? I have some energy levels. It can be electronic energy levels, vibrational energy levels, rotational energy levels, what have you. We say that the ratio of populations between two levels, N1 by N2, is given by e to the power minus E1 minus E2 divided by T, and that T is called excitation temperature. So we have the concept of excitation temperature. Then in astronomy, you introduce one other temperature, which is called as the spin temperature. So these could be various levels of the spin angular momentum split due to an external magnetic field. And the ratio of population between these in thermal equilibrium is given by a Boltzmann distribution, and that T is called as the spin temperature. And then finally, there is the radiation temperature, which is given by Wien's law. These four temperatures are equal if and only if all the degrees of freedom talk to each other sufficiently that they come to thermodynamic equilibrium with one another. And that only happens in a truly opaque body. In most astrophysical situations, you are not dealing with opaque bodies. So there are only two situations that I am able to think of on the top of my head when you dealt with opaque matter. One was the early universe, the first 3 or 4 minutes, and then the interiors of stars. The rest of the universe is pretty transparent today. So true thermodynamic equilibrium is never achieved. Right? So I just wanted you to appreciate that. So I will end on that note. Let me see, is there any other slide? Yeah. No, I'm going backwards. No, I'm going. Why am I going backwards? Why? Something. Now I'm going backwards. Okay. I'm going backwards in order to go forwards. Okay, it's like entering a black hole. So this is next Wednesday's lecture. So I'm happy to take questions on today's lecture. Okay, next Wednesday we'll switch to something different. Yes, don't hesitate to ask. I know these are all simple things, but I think bread and butter things. Okay.
Yeah, raise your hands if you would like.
You said that photon takes about 30,000 years to reach the...
Repeat that.
You said that a photon takes 30,000 years
Yes.
To get from the interior of the sun to the surface of glass scattering. So when we point our spectroscope at the stars, are we seeing them 30,000 years ago? Are we seeing the composition of the stars 30,000 years ago?
No, not really, because what you're seeing is only the outer layers, right? You deduce the composition of the stars from the emission and absorption lines you receive, which are from the outer layers of the atmosphere of the stars, right? And from there, light more or less comes in 8 minutes. So please remember, what was emitted 30,000 years ago is not visible light. That is gamma rays, because some nuclear fusion reaction takes place, and what is emitted is gamma rays. So in this random walk, two things happen. One is direction of the photon gets changed every half a centimeter. Secondly, its energy gets degraded by the second law of thermodynamics. So it's only when it comes near the surface, it has got degraded to visible wavelength. Okay. So you're never seeing the original photon in any case. The photon that you see is many generations later coming right from near the surface. So that's more or less 8 minutes instantaneous.
So how do we see the composition of the interior of the sun?
You don't. You see it very indirectly, because in some stars, you can ask this question next Wednesday, we'll go back, but let me briefly answer it. In some stars, violent convection takes place. So matter from the interior is dredged up to the surface. And therefore, you get a clue of what is happening down there by looking at this matter that has been dredged out. Okay? And that happens mainly in what are called giant stars, giants and supergiants. They are no longer in hydrostatic equilibrium. They become highly convective, like when there's a thunderstorm. People say, it's cooled down yesterday because it rained. It didn't cool down because it rained. It cooled down because before the rain, there was strong convection. Cold air was brought down. Okay? So, does that answer your question?
Yes. I had one more question. Shouldn't we include scattering in those equations, the radiative transfer equation?
See, scattering has been included, because when we call alpha nu, as I said, alpha nu is n into sigma nu. Sigma nu is the scattering cross-section. Why is radiation absorbed? Okay, so scattering is included in that. The physics of alpha nu, finally when you calculate that, that includes scattering. It can include also straightforward absorption, like photoelectric absorption and things like that. Then it could include the Thomson scattering, Compton scattering, Rayleigh scattering, Mie scattering. So scattering processes is what gives rise to absorption. Okay. Here we are still in the pre-quantum era, right? So it's like refractive index. Refractive index is manifestly due to quantum processes. But in classical physics, it's a number. So like that, absorption coefficient is a number. The physics of that came only after quantum mechanics, isn't it? So a real stellar physicist has to calculate this alpha. What makes life simple in stars is most matter is ionized. Therefore, the only scattering that is relevant is scattering of photons by electrons, which is Thomson scattering. So you don't care about composition and quantum mechanics and all that. It's a simple scattering which was described before quantum mechanics. Okay? So that's just a saving grace. But in principle, you have to start with quantum mechanics and calculate. Yeah. Are there other questions? There were some. Yes, behind. Can you pass the microphone there?
Sir, in the Einstein's model, you said by symmetry B is equal to C, but isn't there a basic asymmetry that you are exciting, in one case you are exciting an electron to a higher level,
No.
and in the other case you are like...
Coefficient is not the rates are not the same, because the rates depend on the number, right? So the rates definitely are different, but the coefficient, the argument is that the equation that I wrote down on the board there, where I kept B and C as B and C, then, for example, if you look in Fermi's book on quantum mechanics and so on, or any other book, they will argue that if the relation has to be valid at all temperatures, then B has to be equal to C, independently. Nobody is saying the rates are equal, the coefficients. Because finally, quantum mechanics justifies that. In quantum mechanics, the oscillator strength going from this level to that level, or oscillator strength going from that level to this level are the same. Okay. So the real answer to that had to wait for quantum mechanics. Of course, once you have quantum mechanics, you wouldn't derive through Einstein coefficients anyway. This was 1917. Huh? Please remember that. Niels Bohr, for example, considered this paper by Einstein as a profoundly important. And remember, this came just after general relativity. So even contrasted with that, this was seen as an extremely important paper by Einstein.
Sir, when we use the distribution curve there, so we use Boltzmann curve, like Boltzmann distribution. It's only possible if the particles are independent. There is so much density in the star, so why the Boltzmann curve is valid?
I'm not able to understand your question.
When we use the energy level there curve, we use Boltzmann distribution between the curve.
Yes.
But like the particles are not independent there because there is so much density.
No, I never said anything particle are independent.
So why we can use the Boltzmann curve?
Are you making a distinction between quantum statistics and Boltzmann statistics? Well, the answer to that is very simple. Yes, you can say ultimately everything has to be explained in terms of Bose-Einstein statistics or Fermi-Dirac statistics. But both these statistics, in the limit of low density and high temperature, reduce to Boltzmann distribution. And under the densities and temperatures that obtain there, remember you're dealing with 10 million degrees. Yes, if you're dealing with a piece of copper at 300 degrees, you'll use Fermi-Dirac distribution. So the answer to your question is that all quantum distributions goes over to the classical distribution in the limit of low densities and high temperatures. Okay? So Boltzmann distribution becomes the correct thing to use. Even if you insist on using Fermi-Dirac distribution, you'll find you recover the Boltzmann distribution. Is that answer clear? Yeah. The density is not high.
In the star or say...
In the density inside the sun is the density of water. The average density of the sun is 1.4 grams per cubic centimeter. This is 1 gram per cubic centimeter. In the outer layers of the sun, the density is the same as the density of our atmosphere here in this room. So density is not... so the dense stars, we will deal with that 2 weeks from now. There you have to use quantum mechanics. Those are the white dwarfs and neutron stars. That's a different story, right? We'll come to that.
So in that slide for quantum theory of radiation, you said that spontaneous emission occurs if there is it occurs if there is stimulated emission. Means
No, I didn't say that. I said,
please explain that part.
I said, if there is any emission at all, stimulated emission, there has to be spontaneous emission. That's what I said. You cannot have a situation where you have only stimulated emission but not spontaneous emission.
So, sir, if
You cannot have B not equal to 0 and A equal to 0. That is not allowed. Because if that is the case, then you never get back your Planck's law. That was Einstein's point. Without spontaneous emission, you would not have got Planck's law.
So, sir, if both of them are happening simultaneously, so why are we having a different coefficient for this spontaneous emission?
For a very simple reason. The stimulated emission, the number of transitions depends upon how many incident photons there are. Whereas spontaneous emission does not depend upon the external parameters at all. It only depends on how many atoms are there with you to jump. So that I didn't multiply A by U nu. I multiplied only B and C with U nu. Okay? So is that clear?
From the,
Yes.
the chat, and one is, are there objects in nature which violates the black body limit?
Well, as I said, lasers and masers.
Second, nature, not.
Yes. In nature, see, long before Charlie Towns discovered the ammonia maser, there are masers in interstellar space. So nature made masers long before man made masers. So if you want to include that, yes, perhaps we won't have occasion to talk about them, but in a typical maser, or in a laser, what you have is a cavity with two mirrors on either ends, and you have to have the photon going back and forth multiple times to build up this amplification process. Whereas in astrophysical, so there are no mirrors. So in a single path, you should be able to amplify the signal. But because distances are also vast in astronomy, you have a lot of masers. For example, you've all seen the Orion constellation Orion, the Hunter. There is the Orion Nebula, which you can even see with a good binoculars, a little patch. The Orion Nebula is a very powerful water vapor maser, whose intensity is millions of times more than for other sources. So apart from that, I don't know if anything violates, it better not. If systems in thermal equilibrium violate the black body limit, then I can violate the second law of thermodynamics. Let me repeat once again. I will show up at 9:30 next Wednesday. So if there are questions, I'm quite happy to take them up before the next lecture. You go over the notes and try to redo these derivations once more so that it is etched in your mind and so that it doesn't depend upon memory. Okay? An important question. Are all these things too elementary for you? How many of you think I should jack up the level? Okay. How many of you think the level is just right? So, you're all Goldilocks, right? You all know. How many of you know the story of Goldilocks and three bears? Still, only 3 hands. I have actually met people who don't know the story of Goldilocks and the 3 bears. Huh? Goldilocks the young girl walks into this hut. This mother bear, father bear, and the baby bear. There is porridge on the table. The bears have gone out. This is too hot, this is too cold. And only the baby bear's porridge was the right temperature. So that's why these exoplanets, they call them Goldilocks zones. They are at the right distance from the stars. It's not too hot, not too cold. There may be a chance of life there. So you think the level is just right. Do you want me to write more equations on the board, or are you able to copy down from the slides? Sorry? No, you have to speak to me, not more on the board. It's only a question of time. So what I suggest is, anyway, these slides, I can make them available to you. There's no problem. Okay. I can make the slides available to you. Because if I were to write everything on the board, I'll see to some extent. It can be a mixture like this. This can be on the board, and if there is some algebra, hidden algebra, then we can do that on the board. Is there any other comment anybody would like to make about the nature of the lectures? Am I going too fast or too slow or more or less right? Would you like to ask questions in the middle or in the end? If there is something pressing in the middle, put up your hands. Okay. If there are some things that involve discussion, then we will make a note of the question and come back in the end. Please remember, I am not here to complete any portion like your college teachers, okay? We can stop anywhere we like. The important thing is at the end of it, you get something out of these lectures. Okay? When I started as a teacher a long time ago, so long ago that you'll be shocked if I tell you, my teacher told me the following famous Chinese saying. He said, look, if you give a man a fish, he will have a good meal. If you teach him to fish, he will eat well all his life. So he said, you shouldn't be simply answering all the questions and doing the algebra. You must make it so that you teach them the process of inquiry, how you get to the answer. Because once you learn that, then, so many questions are going to arise in your life, not just with respect to physics and personal life also. So the important thing is how to learn to solve problems. Yeah. So feel free if you want me to change the style, speed, whatever. Okay, we'll meet next.